Guys, you got anything from, we're up through 5-3 now. Blake.
Do you mind doing number 37 from 5.3?
Sure, 37. Okay, let's do this. Oops, this is the wrong class. You're famous. We saw like a minute of your OneNote for, I know, right? It's pretty cool. Jackson saw it right away. It's like, that's yours. Okay. Oops. All right. So here we have the definite integral of x to the e plus e to the x dx. So again, we can think about this as two separate definite integrals. I remember that the antiderivative for x to the n is x to the n plus 1 over n plus 1. Okay with that? Since e is a constant.
Yeah, it is. It is a constant. That's
and the derivative of e to the x, or the antiderivative of e to the x, is just e to the x. And then we'll evaluate that from 0 or 1 to 0. So I have 1 to the e plus 1 over e plus 1 plus e to the first minus 0 to the e plus 1 over e plus 1 plus e to the 0. So if I simplify this down, this is 1 over e plus 1 plus e minus 0 plus 1.
How did that become? How did 1 to the e plus 1 become just 1?
Well, 1 to any power is just 1.
Yes, it is. That's very true.
So, and I would say this would be okay to leave it, or if you wanted to get rid of the 0 even. Oops, that should be minus 1 though, right? Because the negative needs to distribute. But you could drop the 0, obviously. But I wouldn't bother with common denominators or anything. That feels like just a hassle, not worth doing.
Yeah.
Does that feel okay, Blake?
Feels good.
Again, the key there was recognizing that that was just an x to the n.
Yeah.
Mackenzie. Sure. Oops, that's not where that was supposed to show up. Oops. Okay, we have the integral from -1 to 1 of e to the u plus 1 du. So we need the antiderivative of e to the u plus 1. What's the derivative of e to the u plus 1? E to the u plus 1 plus the derivative of u plus 1. And what's the derivative of u plus 1? Just 1. So if the derivative of e to the u plus 1 is e to the u plus 1, what's the antiderivative of e to the u plus 1? E to the u plus 1. Yep. So we just evaluate. So I have e to the 1 plus 1 minus e to the -1 plus 1, which is e squared minus 1. And we're done. Feel okay? Again, the trick was there recognizing that the antiderivative was just itself, which is not so bad in that case, considering we can just like, hey, I wonder what the derivative of this is if the derivative is just itself, since I know the derivative of e to the x is just e to the x. Should it really matter if I put a plus 1 next to the variable? Well, let's check, right? That's what we did. What else do you guys have? Mackenzie? (5.2) number 25? Sure hope so. Let's see. Insert. So I'm going to grab a whole bunch of problems here so that I can read the directions. Okay. Yeah. All right. So this says, use the form of the definition of the integral given in Theorem 4 to evaluate the integral. So I'm going to need, in Theorem 4, I have that the integral is the limit as n approaches infinity of the sum from 1 to n of f of x sub xi delta x. So first things first, I'm going to calculate my delta x. So that's going to be b minus a over n. And then I need my xi, which is a plus I delta x. So that's 0 plus I times 1 over n. Or I'm just going to write that as I over n. So now that I have that, we'll go ahead and use our theorem. And remember that f of x is x cubed minus 3x squared. So let's go ahead and do that. In the interim, I'm going to go ahead and move this outside of the sum, since the sum is depending on i's, and there's no I in that term. So I can move that to there. And then I have f of I over n is I over n cubed minus 3 times I over n squared. That probably should be in a parenthesis there. So far, so good, Mackenzie? Okay. Now I remember that summations can kind of distribute across the subtraction symbol. So I'm going to do that. And a constant can be pulled out front of that summation. So I'm going to do that also at the same time. Okay there. Okay. Now, again, I notice that, hey, this n to the third and this n squared don't have anything to do with i's, so I can pull those in front of their respective summations. Oops. Be 3 over n squared now. Still doing okay, Mac?
Yeah.
Okay. So the next thing you'd recognize is that these two sums are things that we have a formula for. So if I went back and looked that up previously in the chapter, I think they're in one of the front covers of the textbook or the back cover. I don't remember which one, but they're in one of the covers as well. This is n times n plus 1 over 2 squared. And then the sum of I squared is n times n plus 1 times 2n plus 1 all over 6.
These formulas that you just wrote out, you said earlier that we don't have to memorize it. Is this still true?
Yes, still true. Still true. Because we're really never going to use this again, right? The fundamental theorem of calculus makes this obsolete, which is lovely. Okay, so now all I need to do is try to evaluate this limit. I'm going to do some cleanup in order to make that a little bit simpler. So I'm going to go ahead and FOIL this thing out. And then I'm also going to FOIL out the other one. So that's going to be n to the 4th plus 2n cubed plus n squared over 4n to the 4th. And then the other one I'm going to have 6n to the 3rd plus 3n squared plus n all over, that should be a 9, and that should be a 3, sorry, over 6n cubed. Yes, yep, I took that in also, yep, 100%, so I did that as well. That's where it disappeared to, 100%. I just basically multiplied everything out, so I just had two fractions. And here what I'm going to notice is that both of these, if I try to do a direct substitution, are indeterminate forms, right? But the nice part is, notice that the degrees for the polynomials in the numerator and denominator are the same. So if I use L'Hopital, or if I like multiply this one by like 1 over n to the 4th over 1 over n to the 4th, and this one by 1 over n cubed over 1 over n cubed, we'll get we'll be able to evaluate the limit here, get rid of that indeterminate form. And now if I do the limit of a constant is the constant. The limit of constant over variable when we're going to infinity is just 0. So we get negative 3/4 out of that, which I hope is what matched the back of the book. Is that mildly impressive that Mr. Kula can do that on the fly and not make a mistake on it? Of course, yeah. Is that good enough? Is it too small now?
Yes.
Good? Okay. Again, on a test, would I ask you to do something like that? No, I won't ask you to do that. On the test that I've written for you here, you're going to be using, to actually compute an integral, you're not going to be doing the limit of a sum. Okay? If it's an approximation, you can do a Riemann sum and build some rectangles, right? And just calculate the area for the rectangles. If it's just a graph, you can hopefully geometric it out, like turn it into like rectangles and circles and triangles and stuff and just add up the areas. If it's an equation, like this one was, we would just use the fundamental theorem of calculus and antiderivatives to do this. So like this method that we built here was simply to get us to the fundamental theorem of calculus. It's a stepping stone. And I'm not going to ask you to use it because it's like algebraically just like a colossal pain in the tuchus. And I don't think it's that, like after like I think it's valuable to do some example with it so you understand kind of like what this fundamental theorem of calculus is shortcutting us through. But like, what's the value gained of like memorizing all these formulas and like, it's a lot of time for one problem also. Mackenzie? 47 in the same section? Sure. Oops, that's not where I wanted that to go. So it says we want to write this integral as a single integral of the form yada, yada, yada. The tool that I'm going to be using for this is this property number 5. So let me just drop that in so you guys can see what I'm doing. And this is the kind of a problem which I think is perfectly reasonable 5-2 test question. So basically what it's saying is that if I can link the upper bound with one integral to the lower bound of the next integral, I can just piece it together as one integral. It has to be the same function. Right? And then that's all I'm really looking for. Is that cool with that? Yeah. All right. So I'm going to start, and I'm going to go from, let's see here. So pretty obvious how these two can go together, right? Since those are the same, I can go ahead immediately, and just write that as that. Well, look at the equation here. Okay. So I have the integral from a to c plus the integral from c to b becomes just the integral from a to b. So since those two are the same, I can just do the start of one to the end of the second. So that's all I did there. Everybody's okay? So I noticed that these two have the same bound, but one is an up, or both of them are lowers, right? So that's a problem. I can't use that theorem as it's currently written to do that. But I heard Mia mouth what we need to do. We have another property from this chapter. Again, I'll drop it in so you guys can see what I'm doing. It says that I can flip the bounds of my integral just by making it negative. So that's what I'm going to do there. So I'm still going to have this one. And I have my f of x dx. I have my minus sign. And then I'm going to make it this negative from -1 to -2 f of x dx. Everybody's okay there? Now, the negative of a negative makes this a plus. And so now we're going from -1, I'm sorry, since the upper and lower are the same, I can just rewrite this now as the integral from -1 to 5. And that's me done. I think this is a lovely test kind of caliber question from 5.2. It just forces us to use the theorems. It's wholly symbolic. There's no calculation, doesn't take a long time, a lot of space. Just have to understand like how to use these two theorems in conjunction to like take something complicated and reduce it down into something simpler. So this is the kind of thing I think is a wonderful 5.2 kind of test question, which should feel pretty doable, right? Like the calculation is not tedious, it's not super complicated, it doesn't take a lot of time once you see it. You just have to see what to do. And again, it's the two properties from this section that are like the huge ones going forward. Like these come up a lot. You'll use them frequently. They're nice ones to have at hand to get comfortable using, as opposed to what we did on number 25, which I think is like valuable, but like inappropriate for a time test setting because it's just really time consuming question. Mackenzie, does that feel? Okay. Cool. You guys want to do 5.4 here real quick? Okay. 5.4 is a quickie, which is nice. So in section 5.4, we're going to introduce the concept of an indefinite integral. So up until this point, everything we looked at was a definite integral. When we say a definite integral, we mean that we have a lower bound and an upper bound identified. So some a and b. Whether those a and b are constants or they are a variable expression, it doesn't matter. It's still a definite integral. An indefinite integral is going to have no bound at all, no bounds at all. So it's just going to be the integral symbol with no a and b.
Does that like imply that it's going to be going from negative infinity to positive infinity?
It does not.
Okay. No. Okay.
Yep. We'll show you what it means in a moment. So again, remember that the definite integral from the fundamental theorem of calculus part 2 is just the antiderivative evaluated at b minus the antiderivative evaluated at a. The indefinite integral, we just say the integral of f of x dx is the antiderivative of f. And really should be, because it's an antiderivative now only, it's not any antiderivative. That means that these are all going to get the plus c's at the end. We didn't do it before in the fundamental theorem of calculus because in the fundamental theorem of calculus, f was any antiderivative, where we'll just assume the c is 0. Here, it's the general antiderivative, so we need a plus c on that one for the indefinite integral. Is everybody okay with that? All right. So for example, the integral of x squared is the antiderivative of x squared. So that would be x to the 2 plus 1 over 2 plus 1, and then plus c. And we see that if we take the derivative of that, we get the x squared back again. So clearly these are antiderivative of each other. So here we've collected together all of our antiderivative rules along with several of our common integral rules. So the first three are just like, well, the first two, I should say, up here are just basic like integral rules that I can pull a constant out front of my integral, or that I can distribute an integral across an addition or subtraction symbol. Everything else after that is just our antiderivative rule written in the form of an integral. So these are the same antiderivative rules from chapter 4 that you guys hopefully still have memorized, which is lovely, right? I love when we repackage something I already have memorized as to something new, because it's nothing new to do. So let's just do some examples now. So again, I notice immediately that this is an indefinite integral because there are no bounds on my integral symbol. So the first thing I'm going to do is I'm going to distribute my integral to both terms and pull the constants to the front. Oops. Got to be careful there, because notice that the dx applies to both terms, so you have to have a dx at the end of each integral. Everybody's okay with what I did there, just as my first step? Okay. The antiderivative for x to the 4th is x to the 5th over 5. I'll just write it that way so that you can see my work. And really, what should we have here? Plus c. Okay. It doesn't matter because 10 times c is still just a constant. So you don't have to. You could if you wanted to write 10c. It's not wrong. But like, it's a constant. It just is going to like 10 times the constant is still a constant. So like we haven't named what the constant is. Still just a constant. The antiderivative of secant squared is tangent. Excellent. And again, we have plus c. Now, technically speaking, really one is like, they are not the same constant. Probably I call one c1 and the other c2. But here's the thing. When I add c1 and c2, what am I going to call that? I'm just going to call it c. You could call it c3. That's fine. I'm just going to call it c. So what I have 10 times x to the 5th over 5 just becomes 2x to the fifth, and then negative 2 times tangent x is negative 2 tan x. And I'm done. Mia. That's fine. How do you know C2 isn't a negative number? Okay. And C1 and C2 are not the same number, so they're not going to cancel out. Whether you're adding or subtracting them, you still get a constant back, right? So the convention is, regardless of like, oh, is this negative C or positive? It doesn't matter. It's just a constant. You know what I mean? But yeah, sure. But it's one of those like, I didn't mean it as plus a negative number. It's fine. You know what I mean? It's all just constants. So you'd be very hand wavy about it and just put a plus C and it's fine. And in general, for something like this, when I'm doing this, I'm not going to bother doing this. I'm just going to put 1 plus C at the end, right? Like I'm showing you like what's going on, but like, come on now, folks. We're just going to write a plus C when we're done doing the antiderivative. Because probably something like this, at the end of the day, you're not even going to bother showing this step, right? You'll just do the antiderivative of the first piece and the antiderivative of the second piece and put a plus C at the end. You know what I mean? Now, when we're just getting started, yeah, I'm going to do that. Like we're going to show the antiderivatives and really make a big show of it. And make sure that we understand like the properties of the integrals as we're using them. But probably by the end of this chapter, if not the start of the next, you're going to stop kind of doing all that. So it just makes a problem a little bit more. When the problems start getting more tedious, we start eliminating those simple steps. You know what I mean? Just so it doesn't take like a whole sheet of paper if it doesn't have to. All right. What do I do with this? I don't know how to do the integral of a quotient. None of my antiderivatives are quotients. That's exactly right. So Blake says I can rewrite this as that. Everybody cool with what we did there? And that, I believe, is one that we have an antiderivative for, is it not? Do you remember what this is off the top of your head? I never remember these ones either. That is negative cosecant. And we're done. All right. This I'm liking, Mr. Kulik. This is so little work to really write down and show. It's like, get it into a form where I can do something with it, and then we'll just do the antiderivative. Okay, what's this one? That's a definite integral. Does that change my first steps at all? No, man, I'm still just doing antiderivatives. Let's try to simplify or streamline our work a little bit. The antiderivative of x cubed is? Okay, x to the fourth over 4. And then I'm going to do minus 6. And what's the antiderivative of x? X squared over 2. And then we'll just evaluate that from 0 to 3. Notice there's no plus c now. Why is there no plus c? Because it's a definite integral. Excellent. So what do we have there? 81 over 4 minus 27. So 81 over 4 minus 108 over 4. So that's negative 27 over 4. Not too bad, right? No big deal. Very much the same thing we've been doing. All right, let's take a look at this bad mama jamma. Let's write this one out, the sub-steps, since there's kind of a lot going on here. So the first thing I'm going to do is distribute the integral through and pull the constants out front. Does that all look okay to you guys, what I did there? The one that would have been easy to miss would have been that 3. That would have been the one I would have been concerned about you missing had you not done this step. Okay, antiderivative of x cubed is? Over 4. The antiderivative of x is x squared over 2. Excellent. The antiderivative of 1 over x squared plus 1. Tangent inverse. Excellent. And we're going to evaluate that from 0 to 2. Just write it this way. Well, this reduced down, right?
Oh, I didn't know. Okay. I see.
And then I'm distributing the negative here as I go. Here's the good news. 0, 0, tan inverse of 0 is 0. So that end just drops on out of there. So I have 8 minus 12 plus 3 times tan inverse of 2. Now that's not a unit circle value. So I just have like negative 4 plus 3 tan inverse of 2. So I could leave it like that as an exact answer. Or if the back of the book had a decimal, negative 2 plus 3 times tan inverse of 2. Before I type this in, though, what should I check? Yeah, I should be in radian mode. I am. Okay, that's good. So negative 678 or 679. I think either is fine. I mean, if you wrote this step, I would not complain about either of those answers. I think are reasonably appropriate, assuming you have some work to back this one up, and I know you didn't just type it in your calculator. Right, I showed you guys how to do that last time. Type a definite integral in. Yeah, okay. What about this one here? It's like, whoa, that looks like a quotient, Mr. Kulik. I don't know how to do a quotient integral yet. Yeah, you just write this as three separate fractions, right? So this is really the integral of 2 plus square root t minus 1 over t squared. Everybody agree with that? If I do the division. Now, why was this so easy this time? What made it so easy to do that division? The denominator is a monomial, like a single term. If that was a polynomial, like if Mr. Gulick was a jerk and put like a +1 down there, what would you have to do then? Polynomial division. I look at the numerator, I can tell that guy isn't going to factor. You'd have had to polynomial divide that, which is going to be a hassle, but possible.
Do you have to, or is there a way to like?
That would be the fastest way to do it.
Do we know how to do that?
Polynomial division?
No, we know how to do that, right?
Yeah, you learned in your Algebra 2 class.
Yeah.
Do you still remember how to do it? We can do that in a second.
I do, actually.
We can do that in a second. Okay, let's finish this one up first, though. The antiderivative of 2 is, well, it's not x as our variable. It's a t, so we'll do 2t. Yep. What's the antiderivative of the square root of t?
T to the 3 halves over times 2/3.
Yeah, so we'll write it this way, and we'll turn it into 2/3 in a second, just so everybody can kind of see. Maybe we'll write it as 1/2 plus 1, so everybody can see that what we did there. Okay, and what's the antiderivative of 1 over t squared? The only exponent that you can't just do that power rule in reverse for is -1, right? Because that's the natural log. All the rest of them are just using that power rule in reverse, right? So don't get tied up to natural log just every time you see a 1 over. And then we'll evaluate that from 1 to 9. So clean this up a little bit. So we have 2t plus 2/3 t to the 3 over 2 minus, or really plus t to the -1. I'll write it that way. Yes, sir. Certainly. Sure. So 2 times 9 plus 2/3 times 9 to the 3 over 2. Plus 9 to the -1 minus 2 times 1 minus 2/3 1 to the 3 over 2 minus 1 to the -1. What's 2/3 times 9 to the 3 over 2? Should be something you could do in your head. 18 is correct. Well done. So talking through how you did it, the denominator of 2 means square root. Square root of 9 is 3. 3 cubed is 27. Divided by 3 is 9. Times 2 then is 18. Everybody okay? Again, This is a reasonable thing, a reasonable no calculator problem. I just wanted to talk through how you do that again with no calculator by, without having, obviously if you have a calculator, just type it in, but this would be not an unreasonable no calculator problem. And then we have the plus 1 over 9. We have a minus 2, minus 2/3, minus 1. And then it's just, some common denominator crapola. I'm going to skip all that. What do you guys think so far? This is not much different than what we did in the last section, right? In fact, these last two problems are exactly things that we could have done in the last section. The integrals were a little bit more complicated than things we did in the last section, but still things that would have been technically doable. So we have the part 2 of the fundamental theorem of calculus. We can also think about this as like in an application setting. So if we're looking at the net change of something, that's like the accumulation from some rate. So I can do that by just integrating that rate from some starting time to some ending time to get the total amount of accumulated, the net change in some quantity. So like if you have water running out of a container at a specific rate, and we want to find out how much water is run out in over, from time 3 to 10, you can integrate the rate with respect to time from 3 to 10, and it'll give you the quantity of water that is now run out of your container, for example. But really anything that's like an accumulating of a quantity via some rate is a natural integration problem. So let's look at a couple of examples. So here we have that a particle moves along a line so that its velocity at time t is t squared minus t minus 6. Find the displacement of the particle during the period from 1 to t. And then part B says find the distance traveled during this time. So what's the difference between distance and displacement? So let's say that this is our start, and our particle did that. And this is just like one dimension. Let's think about this as just two-dimensional motion. So the end was here. That distance is the displacement. Right? Versus the distance traveled would have been that length is the distance traveled. Everybody's okay with the difference between the two? Displacement is just how far you are from the start, but you could have like gone forwards and backwards a bunch of times and traveled, done a whole bunch of walking, but really ended up with no displacement. Like if I jump out of my chair, run around the school, come back and stop at my chair, the displacement is 0, but I did a lap around the school, so clearly I covered some distance. Does that feel okay vocab-wise? Okay. So what is that going to mean to us? Well, for part A, a velocity is a rate. So to find the total displacement I'm just going to integrate my rate function from 1 to 4. That'll give me the net change in position of my particle. That's the displacement, the net change. Well, that's pretty easy to do. So the antiderivative of t squared is t to the third over 3. The antiderivative of t is t squared over 2. The antiderivative of 6 is 2t, or is 6t. And then I just evaluate from 4 to 1. So whatever that comes out to be, I'm not interested in actually doing the arithmetic right now. But that's the gist of that. Everybody's okay there? Now part B, how do I need to change my integral to turn this in from a displacement into a distance? It's not making it indefinite. Let's think about what would have happened or could have happened here, right? Suppose that like our particle did something like this. So that's like an area going forward, but then that's like an area going backwards that ends up with a displacement at 0. If I want the distance, I need to count that. So I'm going to take the absolute value, 100%. That's 100% right. So to get the distance, I'm going to do the absolute value of that. How do I do the integral of an absolute value? Well, my goal here is I'm going to break this integral up into the positive part, and then I'll plus the negative part. And the negative part will just switch the sign. Everybody's okay with that? So to find the positive and negative parts, I'm going to take my function and figure out where it's negative. Everybody's okay with that? If I think about this then, -2 to 3. That's what my parabola is going to look like. I know it opens up because the leading coefficient is positive. So the negative part on my interval is going to be 1 to 3. Everybody's okay with that? So we'll do the negative integral of 1 to 3 of t squared minus 6 minus t, or minus t, I don't know why I wrote a 6 there, dt, and then plus the integral from 3 to 4 of Does that feel okay? And now this is easy because we know the antiderivatives for each of these already because we did it in part 1. And that piece all needs to be negative. But evaluate that from 1 to 3. And then plus the same antiderivative evaluated from 3 to 4. This looks super annoying to me. So this is how I'm going to do it on my calculator. I'm going to go ahead and just type my antiderivative into the y equals menu. And I'm going to let my calculator do all the substituting in for me. So that's my antiderivative, right? So I'm going to do negative, parenthesis, y1 of 3 minus y1 of 1 plus y1 of 4 minus y1 of 3. And that to me feels like way easier than going and grinding through all the inputs there. You know what I'm saying? Yeah. Cool. Okay. What if we're given something like this? Here it says figure 4 shows the power consumption in the city of San Francisco for a day in September. P is measured in megawatts, so that's the y-axis. T is measured in hours, starting at midnight. Estimate the energy usage on that day. What do I want? Well, the energy usage on that day is going to be the integral of P of t dt from like 0 to 24 or whatever, right? What is it really though? Area under the curve. What would I do? I would just count some boxes. So like, and count up all these boxes. That's 4 by 24. So that's going to be what, 96 of them in there. Agreed? And let's see, we'll do all of these boxes. That's 2 by what? 2, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15. So that's a 30 in there. Oops. I need to erase that. And then we'll count all of these boxes. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And I'll count all of those boxes. 1, 2, 3, 4, 5, 6, 7, 8. And then I'll count anything else that I haven't. So like this looks like a half a box. That looks like maybe 0.2 of a box. I'll call those zeros. And I'm just going to kind of go along and just add all this stuff up. You get the idea at this point, right? I'm going to do no calculus other than the observation that that power rate consumption integrated over the time period is going to be the total energy used. And the way to calculate that is going to be the same as the area under the curve. So I'm just going to be counting boxes at that point. Keep in mind, though, that each box is like 1 by 100, right? So we'd add up all those. Times the area of one box, which is 100. So this will be some number of, was this energy is in like joules or something. What's the watts are like joules per minute? What is it? No, but a watt is like, that's a rate. That's like joules. Physics people or something. Is that a joule per minute or something? Or because that's going to be our energy unit. Let's grab the old Google and see. A watt is joule per second. So this will be some number of like megajoules.
Would you mark that wrong on a test? Color megawatts.
I mean, I don't know. I probably wouldn't give you something as dumb as like an energy rate that's not written as like joules per, like megajoules per, like whatever. Yes, I would not consider that common knowledge. I would probably give you something like, here's the graph of like the speed of something in like meters per second or something, and just like where it's quite obvious what the unit at the end needs to be from the accumulation, whether it's like gallons per minute or I'd write it as like unit per unit, not like watts. Or let's say, what is a watt? Right? Like joules per second. Did we know that? Maybe. I had to Google it. I knew it was joules was the energy unit that was the SI unit to go with watts, but I couldn't remember. It was per second, per minute. What was it? It's a poop load of joules here. It's because a joule's not very much. Okay. Yeah, sorry. But that's the gist of 5.4, right? So these are, I think, pretty easy at least in terms of complexity. Like nothing is getting like crazy complicated here. Like the algebra is pretty light on all this stuff. The number of steps is pretty light. This should feel pretty good, right? In a lot of ways, these integrals are, at least early on, are easier than the derivatives. Or they stay easier for longer anyways. I would say next class, we're going to do the homework quiz. Tentatively, I had it scheduled for today, but that is, I didn't want to do it. That's what it boiled down to. No. Be up through 5.3. It's going to be done on through the MyAP. It's going to be no calculator. I'm going to practice doing some of this no calculator. Now, none of the arithmetic that you're going to have to do is worse than whole number arithmetics. So like it's all stuff that you can do by hand, should be able to do by hand for a student on this level. It's nothing is like, I'm not going to have like the square root of 27 or something in there weird where it's like rewrite as 3 root 3. Nothing even as bad as that. It's just going to be like whole number stuff. Maybe worst case scenario, you might end up running into something like where you have to do that. Which again, like doable. Doable with no calculator. Would you have struggled to look about that one part? Maybe, but probably if you got everything else but that one part, you could have been like, okay, I think it's got to be this answer then. Because I know it's at
Multiple
least,
choice.
yeah, because they're multiple choice questions,
Oh, okay.
right? So you, at least you got something to work from, yeah. I think it's 12 multiple choice questions.
Okay. How long do we get to do those? 12?
To be honest with you, I haven't thought about that. I'd probably say a half hour at least.
Okay. Good thing we,
Yeah, I mean, I went and buzzed through it. I was like a minute per question, but again, I've done this before. I know what I'm doing. Like, it's not the same conversion. It's at least 2 or 3 to 1. Like Mr. Kulik minutes to you guys' minutes
yeah.
on average.
So you guys done the 12 minutes. That's
I didn't really time myself. I just kind of looked at when I started and when I ended. I'm like, okay, that's like a minute per question. It might have been like 13 minutes or 14 minutes, or it might have been 10 minutes. I didn't really.
yeah. You were averaging 1 minute and 8 seconds. Now
Yeah,
1 minute
I mean,
flat.
it's like whatever.
Gotta get that through.
It was quick. It was quick. There's only one that I was like, had to really like think about twice because I didn't get my answer. I couldn't get an answer on the multiple choice on my first pass through, and I was like, what did I do wrong? And I was like, oh, I made this way more complicated than it needed to be. It's like, oh, that's all I need to do. That's a 1 minute question when you see it. So anyways, yeah, so that's next time. I think for the problem set for Sunday, what do you guys think? 5, 2, 3, and 4. We meet again this week, right? It's probably reasonable. I'll make sure that I get the My Notre Dame updated for that. But the big takeaway is try to be through 5-3. And certainly there'll be stuff for the homework quiz that you would need memorized, like you need the antiderivatives, like you need the list of antiderivatives memorized. Now, that shouldn't be a big deal because they're the same things that we did in chapter 4. You'd probably need like those rules that we did this problem with would be good ones to make sure you remembered, that you flip this upper and lower bounds, it makes it negative, or like you can piece 2 integrals together to turn into 1 integral by breaking it at a common upper and lower bound. Those kinds of things. Now, like, you don't have it like memorized to where you write it down, but you want to make sure that you're aware of it. I'm trying to remember if there's another one in there. What else did we get at the end of 5-3? Maybe it was the end of 5-2. There's some. Oh, this stuff, again, I think is good stuff to have at hand. This is good, like, proving non-numeric calculator stuff. But again, it's pretty self-evident that if you have a function that's always positive, its integral, the area under that curve that's always above the x-axis, always has to be a positive area. If you have one function that's always on top or always above another function, the area under the function on top has to be bigger than the area function underneath. Sure, of course. And then if you take the lower bound or the local minimum and the local maximum over some interval, that the area of the rectangle formed by the local minimum, with the local minimum as the height, and the rectangle formed by the local maximum with the height is an upper and lower bound for your integral. Like, that's all these things are saying. Like, knowing all the symbols, I don't think is that necessary, but just like intuiting kind of what they mean, like visually thinking about what that means. That's what we're saying here. I think that would be enough. I don't think that you need to like symbol memorize them. You know what I mean? Like the antiderivative symbol memorized for sure. but like these other theorems that are just like you kind of have to be able to know, just kind of know what you can do and what you can't do, or what you can say and what you can't say, is probably enough. Does that make sense? Okay. I'm going to stop here. We're almost out of time. Do you guys have any last follow-ups for me, or comments, questions, concerns, criticisms? Pace feels okay. We're not doing too fast here. I think this chapter is pretty doable. 5.2 is kind of sucky, but the good part about the parts from 5.2 that we need are not the sucky parts, which is all right. And then 5.5 is the last section. That's probably the trickiest, but it's also the most useful, because in 5.5 we're going to learn a technique for integrating something that was the result of a chain rule. So we're going to learn how to do the antiderivative for a chain rule derivative, which is not too bad, but you have to be kind of sneaky sometimes in getting something to work. But that's what we'll do next time after we do the quiz, or maybe we'll do the stuff first and the quiz second. I haven't decided. I'll let you guys pick. Seems fair, right?